Jake Woosley is coming to class today. So we have 5 in here, 6, 7. That would make 8 if Jake is coming online. So I think we're all here. So again, what I want to do today is just continue talking about this math kind of stuff. And we're soon in section 3 really going to integrate it with our knowledge of quantum mechanics. But we want to sort of build up the pieces, understand, technically speaking, what a Hilbert space is, which you probably heard about in modern physics, but we want to know more definitely what it means. And so we were talking about a vector space, a collection of vector spaces. And for our vector space representing states of particles, maybe in one dimension, we have several ways of representing those vectors. One is with functions of x. Usually, if we're representing a single particle, we want it to be a normalizable function of x, so we call that a square integrable function. And the vector space we'll be talking about is the set of all square integrable functions. But, we could expand in some basis and use those coefficients in the expansion as a description of the vector space. And we usually call that description little L2. That's the set of square summable sequences. And later on, we'll be talking about spin, and we'll be using finite dimensional vector spaces. But I just wanted to remind you that, we have this way of thinking of vectors as column vectors, and all 3 of these we can sort of think of as column vectors. Little L2 has an infinite number of components in the column vector, and for capital L2 we're talking about some continuous collection of components there, one for each x value. Think of the value of the function at each x as like the component at that x. We will, at the end of last time, we were talking about the norm. We'll always use a norm in quantum mechanics that's derived from the inner product. So to find the norm just means the length of the vector, and the norm is the square root of the inner product of the vector with itself. You're probably familiar with that before. And I just wanted to point out that that helps us make sense of this positive definiteness kind of axiom that has to be satisfied for any inner product. One way to think of this is that now that we know the inner product is related to the norm, this is just the square of the norm of the vector x. And this last one is the statement that this is an equality, not an inequality, but it equals 0 only for the 0 vector. So that's saying now that we're only going to let the length of a vector be 0 if that vector is the 0 vector. We shouldn't have any non-zero vectors have a length of 0. That kind of makes intuitive sense. So hopefully, I don't think I said that last time, so I wanted to sneak that in there. And where we ended was we were working through these example problems where you're just supposed to calculate some things and then come up with some examples too. And this, I think, is where we ended up. Here we're supposed to calculate an inner product and a norm. So here are 2 vectors in little L2. Little L2 is the set of square summable sequences. Hey, these look like they're going to be geometric series when I sum up the magnitude of the squares of the coefficients. So it kind of seems like we're talking about things that are square summable sequences there. So let's calculate the inner product between W and V. It's W is the one that needs the star on it, always the first one in the inner product. So that means that I that's in here turns into a minus I, and we just multiply the minus I over the 3 to the n times the 1 over 2 to the n, multiply the components, then add them to the multiplication of the next component. Same thing we usually do, except we just need that extra star on there. So we get a factor of minus I, which I left out of my solution for some reason. And we get 1 over 2 to the n times 1 over 3 to the n is 1 over 6 to the n, or 1/6 to the n. And that's a geometric series for which we can use that geometric series summation formula. When you're summing from 0 to infinity of x to the n, the formula is 1 over 1 minus x. As long as x is between 0 and 1, it will converge. So 1/6 is good. 1 minus 1/6 is 5/6, and 1 over that is 6/5. So we get minus I times 6/5 for that. Nothing interesting about that. We're just practicing turning the crank there, because you're going to see these appear in, these kind of calculations appear in examples, and you don't want to get lost in like, what are we talking about? Oh, that's just what the inner product means on little l2. Similarly, the norm of the vector v. So forget about w. Here's v over here. We need to take the inner product of that vector with itself. Here, there's no i's in v, so I don't have to worry about the stars, but 1 over 2 to the n times 1 over 2 to the n is 1 over 4 to the n, so that's 1/4 to the n. Again, I can use the geometric series formula. Just don't forget to take the square root at the end, right? You've calculated the inner product of a vector with itself, but then you got to take the square root if you're talking about the norm that we're going to use in quantum mechanics. Okay, and I think that's kind of where we stopped, but we were supposed to do 5 and 6, and let's just go through those here on my written solution. Here are vectors in capital L2. Capital L2 is the collection of square integrable functions. Those are the normalizable single particle states, if you like it, that we're going to use in quantum mechanics. So here's a Gaussian function, that's V. W, if I were to write this again, I would use that double arrow rather than equals. It's a little bit lowbrow to say an abstract vector is equal to a function. But in any case, I changed my mind about this function. It's x cubed times e to the minus x squared is what w is supposed to be. So we do w star, this function star times v, and integrate from minus infinity to infinity. I don't have to think too hard because this is an even function. This is an odd function. So the whole integrand is odd, and we're integrating over symmetric limits. So it's 0 in this case. And for the norm of v, we just put this next to itself and integrate from minus infinity to infinity and take the square root. And I think we did that in a previous worksheet problem anyways. Finally, on this is supposed to say C3 there, and I believe I changed it on your worksheet. This is a vector in C3, not C2, but inner product is just what you would have done before, except you need that star and whatever one is first in the inner product, because these are inherently complex components there. And calculating the norm of this vector v, we take the inner product with itself. We do 1 times 1 star plus 2i times 2i star, which is 4, plus 3 times 3 star, which is 9. And then we take the square root of that to get root 14. Nothing dramatic going on there, but there's just a lot of ways we got to learn to turn that crank, and you're going to see all this integrated together in the, starting in section 3 and beyond. Any questions on those examples? Yeah, Yishen. I'm sorry, this one right here, you're saying I have an error. So I have, let's see. Yes, so this is -4 plus 1. This looks like a -4 and a plus 1 gives me -3. I times I is -1. Oh, you're right. Yeah. When I took my inner product, it was 0 times 1 should be 0. Yes, so Yichen is right. This one isn't here, and that makes this a -4. I think that's the third mistake that's been found on this set of solutions. I clearly have to rewrite them. Okay. Good. Now, I think I mentioned this, although we went back to do those problems. What is a complete collection of vectors? Complete collection of vectors means that it's usually a subset of the vector space. So you're taking some collection of vectors, maybe an infinite collection, but still usually not the whole vector space, such that any vector in the vector space can be written as a linear combination of vectors in the collection. So that would be like, for us, we've already seen that for the set of square integrable functions, the psi n's for the simple harmonic oscillator are a complete collection of vectors. They certainly don't comprise all the square integrable functions, but any square integrable function, that has some finite area under the curve after we square it, can be written as a linear combination of the psi n's for the simple harmonic oscillator potential. Okay, so that's kind of the idea that we want to generalize here. Completeness means you're not missing any. It can be too big. Your collection can have too many vectors in it, but it can't have too few to express it, right? If we're in 3 dimensions, x hat and y hat aren't enough. You need a third linearly independent vector. X hat, y hat, and x hat plus y hat aren't enough if you're in a 3-dimensional vector space, right? But x hat, y hat, and z hat would be complete. X hat, y hat, z hat, and x hat plus z hat would be a complete collection. Sort of has too many vectors in it, but that's okay. It's still complete. So that's the idea of completeness. And here's a problem that I want you to help me think of rather than working it out sort of independently. Let's just come up with several examples of this. An example of a complete collection of vectors in little L2, the set of square summable sequences. Can anybody help me write some on the board here? So let's write down some examples of vectors in little L2. What's an example of a vector in little L2? We already wrote some, I think, earlier on in this worksheet, but just give me some examples of square summable sequences. So it's got to be a sequence of complex numbers. And we've got to be sure that it's square summable, even though there could be elements where it might be hard to tell it's square summable. We want to give examples that we're sure of. 1 over 2 to the n. So that would be like 1 over 2 to the 0, which is 1, then 1 over 2 to the 1, 1 over 2 to the 2, and so on. If I square these up and add them, they're certainly going to converge faster than the geometric series 1 over 2 to the n. So that's a good element. So I need to be, when I have this kind of thing, I need to be able to write it as a linear combination of the collection that we're going to specify. It has to be able to be written as a linear combination of that collection. Anybody have an idea for how we might make a collection of vectors? So this is just one vector. Clearly, it's not enough. I want to write a big collection of vectors. Each one of the vectors is going to be one of these things. Anybody have an idea for how we might have enough of them so that any vector, including this one, could be written as a linear, infinite linear combination of them? Well, it might be easier if we start with the one that's actually third on the sheet. Suppose we had a complex 3-dimensional vector space. So our typical vectors are going to be things like 1, 2i, 7. That's a typical element of that vector space, right? What would be a collection of vectors that might be the usual ones that you would choose for such a vector space, right? That might correspond to our x hat, y hat, and z hat, but I want to write x hat, y hat, and z hat in this form in terms of components. What would x hat be in terms of components? In the usual way of writing it, right? Where this is the x hat component, this is the y hat component, this is the z hat component. How would I write x hat in terms of that notation? 1, 0, 0. And then y hat would be 0, 1, 0, right? It's just like column vectors kind of thing, right? And then 0, 0, 1. Am I writing too far over? Yes, sorry. I'm writing too far over for people to see. And I'm not sure if this is auto-focusing on all the plane over here, but we're trying to look at this stuff. Hopefully, if you guys zoom in or open up that window a little bit, you can see it. 1, 0, 0, 0, 1, 0, and 0, 0, 1 That's a collection of 3 vectors, and any vector, such as this one, could be written as 1 times 1, 0, 0, plus 2i times 0, 1, 0, plus 7 times 0, 0, 1. And you can imagine any triplet you write down could be decomposed that way. And so therefore, we would say that this is a complete collection of vectors for this vector space. Right? Now it has just the right number. I could also throw in some other ones. Maybe I'm going to throw in 2, 1, 0. Now I've got 4 vectors in there, and you might say, well, that's too many. We didn't need that one. Well, that's okay. We still call it complete as long as you can write every vector as a linear combination of them. If you have some extras in there, it's still perfectly complete. All right, given that analogy, now instead of a 3-dimensional or a 4-dimensional, we've got an infinite dimensional vector space. Anybody have an idea for what our collection of vectors might look like? Or at least an easy one to write down. Exactly analogous to that case, which maybe we're more familiar with. Yeah, so let's start out with 1 and then 0, 0, 0, and so on. Okay. 0, 1, 0, 0, 0, and so on. And 0, 0, 1, 0, 0, 0, so on. And so on. That's an infinite collection. We need an infinite collection. This is little L2 is an infinite dimensional vector space. And this is kind of a minimal collection. It has just the right numbers. And it's pretty clear how I would write this, right? This would be 1 times this vector plus 1/2 times this vector plus 1/4 times this vector, and so on. So I could decompose it that way. So this would be an example of a complete collection of vectors in little L2. Okay, and I can throw in extras, you know, if I put in a 1, 1, 0, 0, 0. It's true I could have already written this one as a linear combination of those, but I threw in an extra. It's still complete. It doesn't have to be a minimal set to be complete. Okay, you can also be kind of a maximalist. You could say one complete collection that's not very interesting is the whole vector space itself, right? There I've thrown everything in. Of course it's complete because every vector in it can be written as 1 times it's the same vector. Okay, but that's we're usually not concerned with things that are so big like that. Okay, let's go back. I think the other one we want to, oh, I forgot I don't have that connected. The other one we wanted to look at was capital L2. Let me just arrow forward. Okay, so there was the one we came up with. You can throw in an extra one. You could also make different ones, right? This is sort of, this one that I've got up at the top of the slide there is kind of analogous to in a 3-dimensional vector space saying, hey, I don't need to take x hat, y hat, and z hat. I could take x hat plus y hat, and x hat plus y hat plus z hat. Those, as long as they're 3 linearly independent vectors in a 3-dimensional vector space, that's a perfectly good collection that has enough. And I could even throw more in there that I don't need. But, you know, so that's a lot of examples there. Okay, what about in capital L2? Well, in capital L2, we have to be a little bit more creative. We can't argue just by analogy so easily with what we know from finite dimensional vector spaces. But we do know that our simple harmonic oscillator time-independent Schrodinger equation solutions, those definite energy states seem to comprise a complete collection of vectors, a subset of the square integrable functions. Certainly not all the square integrable functions are in that collection there, but it's enough so that any square integrable function is supposed to be able to be written as a linear, infinite linear combination of those. What about some other examples? And I should have said here, I don't think I don't know if I wrote this on your version, but at least in my solutions, I didn't put minus infinity to infinity there. For capital L2, you have to say the range over which you're going to integrate. Here I want any square integral function that's defined on the real number line, right? Between minus infinity to infinity. You might be concerned with only integrating only from 0 to 7 or something like that. That would be kind of like the infinite square well one, where certainly the infinite square well TISE solutions are not going to be a complete set of functions for square integral functions on the whole real number line, because those functions are all 0 outside of where the well goes to 0. But they would be considered a complete set of functions on the range from 0 to a. What about for the complete real number line? If I say I have any square integrable function, here's one collection I've got written up there, the simple harmonic oscillator solutions to the time-independent Schrodinger equation. Anything else we could write down? Sine and cosine. Well, I'm not sure what you mean by sine and cosine. Let's suppose I said, here's my collection. Let me just try to flesh out what you're saying. Sine of x, cosine of x. Okay, now you tell me how you want to alter that. Okay, so and sine of nkx, I'm not sure what k is, but you can tell me about that in a minute. Cosine of nkx, maybe from n equals something to infinity. So you want an infinite collection. Certainly you're going to need an infinite collection if you have any hope. Now, what about these functions? Are these functions elements of capital L2? Are they square integrable functions? Do they have a finite integral from minus infinity to infinity when you take the magnitude squared of this function? No, there's an infinite area under this curve and this one. So it seems like we're in a little bit of trouble there with those functions. They're actually not elements of capital L2. Notice these psi n of x right here, they are, they have that Gaussian function with a little polynomial wiggling underneath it. So they're perfectly okay. And they tend to get wider and wider and wider, so you can represent more and more functions that have area further and further out from the origin. I've lost my cap for this. I really want to recap this pen. I don't know where I put it. Did I put it in my pocket? No. It's unfortunate. Well, I'll keep gesturing with it. Hopefully it doesn't completely dry out by the time I run into it. But, the hope is, and the claim is that Griffiths made, and we'll never actually prove this in the book, that if you have any potential that eventually goes up to infinity on both sides, just like the harmonic oscillator did, such as maybe an x to the 4th potential rather than a quadratic potential, we could have a quartic potential. It would eventually go up to plus infinity, and that means it doesn't have any scattering states. It has an infinite collection of bound states of higher and higher energy. The claim is that no matter what potential you choose, as long as it has all bound states like that, so the collection might be the psi n of x for the potential being x to the 4th, and I guess I should, for the sake of the video, unshare this. I'm being a little bit sketchy here, but there's an infinite collection of these. We haven't found them. Maybe you're going to find them as part of your MATLAB stuff that you're doing, right? Maybe you're going to use this potential. I could choose some other potential, as long as it doesn't even have to be symmetric, right? The claim is that any one of those, right? And even if I have too many, I could take all the psi n of x for x to the 4th and all the psi n of x for x squared, and then I would have way too many functions, but still complete set. That kind of idea. That is the idea. Let me see if I put any more on here. I can't remember what I put in the slides. Okay, so the x to the fourth time independent Schrodinger equation solutions, the collection, which is the union of the x squared and x to the fourth time independent Schrodinger equation solutions. You know, I'm not being too creative there with how I'm putting them together, but that's basically the idea. We're going to solve the time independent Schrodinger equation, and if it has nothing but bound states, those will all be square integrable functions, and they will be enough to write any function as a linear combination of those, right? And we could take other odd combinations, right? Psi 0 plus psi 1, then psi 1 plus psi 2 for one of these infinite collections. It's just a different way, a different kind of, you know, collection of things that it might not be easy to write an arbitrary function as a linear combination of those, but you got to make sure you have enough. Okay, and then in C3, we already talked about lots of, you know, certainly the entire vector space itself is always a complete collection of vectors within the vector space, but not a very interesting one. Okay, so that's a complete collection of vectors. It means we have enough to write any vector as a linear combination of the vectors in the collection. An orthonormal collection of vectors has to be a collection of vectors that are all normalized and all mutually orthogonal, right? So each one's inner product with itself is 1, and its inner product with the other ones is 0. So if we have a discrete collection of them, right? If I say, well, maybe I've got this written in here. Let's see. If I've got a discrete collection of them, like here, I'm imagining I've got a collection of vectors in some vector space for, you know, for I equals maybe 1 to infinity or from 1 to 7 or something like that. Then when we say they're orthonormal, that's equivalent to saying the inner product of Vi with Vj is delta Ij, right? If it's the same vector, that would be where the indices are the same, and that's where that Kronecker delta gives a 1. And if the indices are different, then they should be orthogonal, and that's when the delta gives a 0. So this is telling us they're orthonormal when we write down that relationship. Similarly, if we have a continuous collection, you know, sometimes these aren't vectors in our vector space, but here I'm not so concerned about them being vectors in this vector space. Maybe I've got some vectors vk, where k is a continuous index, as we saw for the free particle. We'll also say they're Dirac orthonormal if you take the inner product between vk and vk prime, and you get delta of k minus k prime. We'll see that appear later on too. Okay, so that's what it means to be an orthonormal collection of vectors. So in our normal vector, everyday vector space, x hat and y hat, if we're talking about three-dimensional vector space, the collection x hat and y hat is an orthonormal collection because they're both they're unit vectors and they're mutually orthogonal. It's not a complete orthonormal collection, but it is an orthonormal collection. X hat, y hat, and z hat would be. X hat and x hat plus y hat would not be an orthonormal collection because they're not perpendicular or orthogonal to each other. Okay, where are we going with all this? Oh, apparently we're supposed to do problem number 8 on the worksheet. Let's look at what that is. This is the two-sided worksheet that is asking in number 8, give an example of an orthonormal collections of vectors in L2 that's not complete. I'm really annoyed that I can't put the cap on this pen. How did I lose it? I didn't walk away from the board. It's got to be hidden here somewhere. So maybe we can just use our work that we already have here. So let me arrow forward here. I probably got my solutions here. An orthonormal collection of vectors in little l2 that's not complete. Well, look, here was a complete collection, and they also happen to be normalized, and they also happen to be orthogonal to each other, right? If I take the inner product of the first vector with the second vector, I'll get 0. You have to think about the definition of the inner product, but the same is true for any two different elements here. So they're all orthogonal and normalized, and therefore, if I don't want a complete collection, I could just take the first 2 elements or the first 10 elements of this one. And it wouldn't be complete, but they certainly are mutually orthogonal and normalized. Same thing for these. After we've already normalized them, if we just took the first 2 of them, that wouldn't be enough to be complete, but it would be an orthonormal collection in that vector space. And the first 2 of these, certainly they're orthonormal, but they're not enough to write any vector in 3 dimensions as a linear combination, and so wouldn't be complete. That was just to force you to think about these 2 definitions. Any questions about those or other examples you want to talk about? All right. Now, let's put these things together. Clearly, too many vectors isn't so interesting, and orthonormal collections that don't have enough in them aren't so interesting. But if we put them together and we say we want something that's complete, and yet all the vectors are mutually orthogonal and normalized, that's going to be a very useful thing. And that's what we're used to, right? That would be like our collection x hat, y hat, z hat in 3 dimensions. They're enough, and they're all mutually orthogonal and normalized. They're going to be very convenient for us. We call that an orthonormal basis. Okay. And let's talk about an example of how to create an orthonormal basis if you have a collection of vectors that is complete but not normalized or orthogonal. Did I bring my notes on this? Yeah, here we go. Let me switch to the board and we'll do this on the board. Okay. So let's imagine I'm concerned with the following vector space. I want to find an orthonormal basis for the vector space capital L2 on the interval from -1 to 1. That means functions that are square integrable when we integrate from -1 to 1. And well, here's a collection of functions that certainly is a complete collection. We know that, I guess, you know, I know this because, well, let's write it down. Power functions, right? The collection, here's a function, 1. It's just defined as 1 between -1 and 1. Here's the vector x, which is defined as the vector, the function x between -1 and 1, x squared, x cubed, x to the 4th, and so on, all the power functions. Now, are these normalized? Well, we could try. If I integrate, you know, for example, if we ask ourselves, is the vector x normalized? That's asking the question, is the integral from -1 to 1 of x squared dx, which would be the inner product of this vector with itself, is it equal to 1? Well, it seems kind of unlikely, right? We're going to get an x squared over 2, 1/2 plus 1/2. This one actually is normalized, it looks like, right? If I did that correctly in my head, right? I get an x, no, I get an x cubed over 3, so it's not normalized, right? I would get a 1/3 plus 1/3 is 2/3. So it's not normalized. And you'll find out if you take an inner product between pairs of these, they're generally not orthogonal either. But you know, from our work in calculus with Taylor series, you can write a lot of functions as an infinite linear combination of these. That would be just like writing their Taylor series expansion that happened to be valid on -1 to 1. So it seems like this is enough to represent all the functions we want. It's just not an orthonormal collection. And we want to learn how to create out of this an orthonormal collection. And there's a method that people use called the Gram-Schmidt orthonormalization. procedure. And we're going to do it on this set of functions and create out of this an orthonormalized collection of functions. They won't be power functions anymore, but they will be polynomials of increasing degree as we go on. Okay, so let's talk about how to do this. And it's easiest to think about it, just in terms of vectors as we understand them in 3 dimensions, to argue by analogy. So what we're going to do is take the vectors one at a time. And I'm going to first say, well, let's say we got to normalize this first one. How am I going to normalize this first function? Well, let's just think of a collection of vectors first, without doing it to this collection. Let's imagine I've got a collection of vectors that is complete. Let's call them v1, v2, v3, and so on. Maybe we're in a very high dimensional vector space, so we've got a bunch of these. How am I going to turn this into a collection of mutually orthonormal vectors? I might call this u1 hat. I'll put a hat on it because it's supposed to be normalized, right? u2, which is orthogonal to u1. u3, which is orthogonal to u1 and u2, and so on. The procedure we're going to describe is going to allow us to turn this into such a collection just by working with the elements we're given. So here's how the Gram-Schmidt method works. What you do first is say, well, if I just start with one of these, the only problem is it's probably not normalized. So let's normalize it. So our first one, u1 hat, is just going to be the vector v1, but we're going to divide by the norm of v1. Then it'll be normalized. And since there's only one vector, I don't have to worry about orthogonal yet. Okay, for the second vector, what I've got to do is, before I normalize, I better make sure I get a vector that's orthogonal to u1. So here's how we're going to do it. We'll normalize in just a minute. The first thing I'm going to do is create a vector u2 that I'm sure is orthogonal to this one. And I'm not going to put a hat on it yet because it's not going to be normalized. Here's how we'll do it. We'll take v2 and we'll subtract out the inner product of v2 with u1 hat. We'll take, and that's a number, we'll take that scalar multiple of u1 hat. Okay, what does that look like in a picture maybe? That means, like, let's imagine here's my normalized u1 hat here. And let's imagine that, well, let me draw this as maybe longer. There's my normalized u1 hat. And let's imagine that v2 happens to look like this. What we're doing is taking the inner product of v2 with this unit vector. And if you think geometrically, this distance right here is going to be v2 dot u1 hat. And then since this is a unit vector, when I take that magnitude times u1 hat, it's going to be a vector along the direction of u1 hat. Maybe I need another color here. This vector going directly to the right is going to be v2 dot u1 hat multiplied by u1 hat, scalar multiplying u1 hat. I guess I shouldn't be using our old notation. Let's use the new notation for inner product. Same thing here. Okay, and then if I take this vector and subtract out this vector, I'm going to be left over with this vector, right? Because the sum of these two vectors is this vector. If I take this vector and subtract out this vector, I'll be left with this one. So this vector right here is going to be v2 minus v2 inner product with u1 hat, scalar multiplying u1 hat. And that vector is guaranteed to be orthogonal to the first one in the series. Okay, if you just look at the formula, it's sort of befuddling. But if you construct it just with pictures, you kind of can figure out what to do. Yichen? Yeah, so let's show that this vector is orthogonal to u1 hat. Here's what happens. Let's take this vector v2 minus v2 inner product with u1 in the order that I said to do the inner product with u1. And let's take the inner product of that with u1 and let's see what happens. Now you have to go back to those, how to distribute things within an inner product. Right here, I got a linear combination. If you think about inner products, you can just say, well, this is equal to, go back to the axioms of inner products. This is equal to the inner product of V2 with U1 minus, here's a number, I can just factor that out of the inner product. The inner product of V2 with U1 hat times the inner product of U1 hat with U1 hat. And this is 1. We already normalized it, right? And these two things exactly cancel. So in this case, I've made it so that maybe I'm not answering your question. I want to make sure the people at home can actually see. Oh, no, they can see over there. Okay. So this is exactly 0. Now, if we had switched the order of this, is what you're asking about, right? Then we would have had a V2 U1 here and a U1 V2 there, and it would not have necessarily subtracted to 0. And how am I to think about that? I mean, everything's working out kind of nicely here. But you're saying, I'd like to take one definition for this, but then when I take the inner product the second time, I'm going to do it in the opposite order or something like that, right?
Yeah, I'm more like, what is the geometrical meaning in our vector? Because in the real vector space, the projection.
Yes.
And it doesn't matter which order you do it, it's just the same.
Yes.
For normal vector. Normalized vector.
Yeah, I mean, I don't have a good, and in fact, this should be, I'm switching notations here. That should technically be aligned with the notation we're using there. Let me think about it. We'll sharpen that up a little bit each end about which order to take the inner product, because it does matter here, but this is the correct way to do it for the Gram-Schmidt method. Okay, and then of course, once I've got that vector, I can just say, oh, the one we're after, U2 hat, is just U2 vector divided by the norm of U2 vector, right? And now you see the procedure. Okay, let me just write down the third one. We're gonna, to get a third vector in my collection, U3 hat, we're first gonna define a U3 vector, which is equal to V3 minus the inner product of V3 with U1, U1 hat, scalar multiplied by U1 hat, also minus the inner product of V3 with U2 hat, scalar multiplying U2 hat. We're subtracting out its projection onto all the other unit vectors that we've created so far. And then finally, we'll normalize. U3 hat is equal to U3 vector divided by the magnitude of U3 vector. That's called the Gram-Schmidt method. And generally, it's a huge pain. You have to do it one step at a time. You could do it for the first 3 of these, right? And you'd end up doing a bunch of very easy integrals of power functions and things like that. But it's still kind of a pain to keep track of everything and then normalize and all that kind of stuff. And we'll encounter actually these orthonormal collection of polynomials of increasing degree on the interval from -1 to 1 when we talk about the solution to the hydrogen atom. They're called the Legendre polynomials. And they actually are, if you take the power functions and use the Gram-Schmidt method on them, you'll end up with Legendre polynomials of degree n, where n is 0 and then 1 and then 2 and so on. So we'll see those later on. Okay, that was just a side note about Gram-Schmidt. You'll see it mentioned, maybe used even in an example in Griffiths, but not a lot of information in there. Okay, and then we want to look at problem number 9 on here, the last one on this worksheet. Give an example of an orthonormal basis in little l2, capital L2 from -infinity to infinity, and C3, the same ones we've been doing. And the answer is, well, we already wrote them down. If you just look, I didn't have to make an orthonormal basis up here, but I happened to use examples that had just enough elements. They were all already normalized and they were all already mutually orthogonal to each other. So my examples in 7 certainly work for these down here. They're an orthonormal basis. There's enough of them to be complete, but they're also all normalized and all mutually orthogonal. Okay, that's not to say they're the only orthonormal basis. They're just the most obvious ones to write down. Any questions on that stuff? All right. Now, let me check the time. Oh, wow. 9:46. Okay. So we'll go about another 15 minutes. Now, we're heading towards the idea of a Hilbert space. Oh, I found the missing cap. It was in my pocket. Good. I knew it had to be close at hand because I hadn't walked away from the board.
I mean, if it makes you feel better, I lost items and then found out that they were literally in my hand. So
Yes. Yes, it's like looking for the glasses on your face. Okay, so we're going to define something now that's the same words getting recycled here, but actually means something quite different. We talked about the completeness of a collection of vectors within a vector space, and now we're going to develop the idea of completeness of a vector space itself. And this is a little bit subtle. It's something that comes into, if you maybe you'll talk about it if you ever take the real analysis course here at Centre College. It's an analysis concept. And the idea is, even though you think you have a perfectly good vector space, you can take linear combinations of things within the vector space and you get other things within the vector space. There might be a sense in which some vectors are missing from the vector space, in the sense that, you could define a sequence of vectors within the vector space that seem to be getting closer and closer to each other, closer and closer to something, but then when you look at it, that something is not an element of your vector space. We don't want that to happen because we want to be able to write down things that look like this, right? So here I'm saying, here's kind of an orthonormal basis for our vector space L2 -infinity to infinity. And I'd like to be able to write down something like this without worrying too much. As long as those CNs are such that the sum from n equals 0 to infinity of the magnitude Cn squared is finite, then this ought to converge to something. But I want to make sure that my vector space is such that, maybe when I form something like this, it's not technically an element of my vector space. Okay, so we want to think about sequences of vectors that seem like they're getting closer and closer to something. If they seem like they're getting closer and closer to something, we need to develop this concept. They should converge, but the question is, do they converge to a vector in the vector space? Okay, and when we're talking about series converging, the definition of a series converging, back when you talked about infinite series, is that means the sequence of partial sums, right? The sum from 0 to 0, the sum from 0 to 1, the sum from 0 to 2. Each one of those defines a vector, and we want those vectors and vectors that are getting closer and closer to something. That something should be in our vector space. So we're, when we talk about a series, there's an implied sequence associated with the series, which is the sequence of partial sums. Okay, so if we're going to define what should converge means, we need a notion of what it means for vectors to get closer and closer and closer together on a vector space. If you want to say close together, you need a notion of distance on your vector space. And there's a natural notion of distance. Okay, so going back to our norm stuff that we had before, we're going to say the distance between two vectors is just the length of the difference between the two vectors, right? If I go and think again in a two-dimensional vector space, here's the plane. See, I think I used up too much of that juice in that pen. Here's the plane, the XY axes, and I might say, oh, here's a vector, and maybe the vectors are pointing to locations in the plane, right? So here's one vector. Here's another vector. When we want to say how far apart are those vectors when we place their tails at the origin, what we really want to say is how far apart are the tips when we place the tails at the same place, right? So if I say this is V2 down here, and this is V1, then V2 minus V1, as you know from your introductory kind of vector stuff, points from the tip of one vector to the tip of the other one. And how far apart these vectors are, we're just going to say, well, how big, how long is that vector? That's the norm. So that's going to be our notion of distance on the vector space. And we're going to use that. Okay. So that's our notion of distance. And then here's the example of a sequence that should converge or ought to converge. It's called a Cauchy sequence. If you take real analysis, you'll probably learn about Cauchy sequences at some point in there. It's a sequence of vectors. We usually think of an infinite sequence of vectors. And if you take the first 50 vectors, there's some leftover tail at the end of the sequence. And a Cauchy sequence is one that, if I say, you give me a small number, 1/50th. It's a Cauchy sequence if this infinite collection of vectors, there's some point where everything left in the tail is all within 1/50th of each other, right? You take any two vectors from the infinite tail that's left over after I've thrown the first so many away, and they're all within some distance of each other. If you give me the number 1/1,000,000th, I should be able to say, oh, throw away the first billion of those vectors, but then the ones that are left over, the infinite number in the tail, should all be within 1/1,000,000th distance of each other, and so on. No matter what number you give me, no matter how small, no matter what epsilon you give me, eventually the tail is all within epsilon. So those vectors are getting closer and closer and closer together. That's the notion of something that ought to converge. It's zeroing in on something in the vector space. And the only question is, well, if it's zeroing in on something, is that something in your vector space? And it depends on how you defined your vector space. If it's not in the vector space, we wouldn't even say it converges, because usually when people say converges, they mean converge to something in the vector space, because when you're a mathematician, you say you define the vector space, and that's my whole world. There's nothing outside the vector space, right? Even though, it's sometimes in the world of physicists, we're thinking of some larger space of functions or something like that. So the notion of a complete vector space, and this is usually very hard to prove for any vector space. A complete vector space is one where every Cauchy sequence of vectors converges within that vector space. So you can write down things that appear like they're converging, and they're going to converge to something in your vector space. All right, let's do some examples of complete let's start out with an incomplete vector space and show an example of a Cauchy sequence. And then I'll just reassure you that the usual ones we're going to use in quantum mechanics actually are complete vector spaces. Little L2 is a complete vector space. Capital L2 is a complete vector space. All finite dimensional vector spaces are complete. So everything we're going to encounter in quantum mechanics is complete. But just to kind of illustrate it, let's take this example. here is my vector space. We'll call my vector space V. It's going to be the collection of all continuous functions of x. On, minus infinity is less than x less than infinity on the real number line. Okay, that's very familiar to us, right? Anyone, don't have to be normalizable. I'm not saying anything about finite area under the curve or anything. Any continuous function, so sine and cosine would be in there, right? If it's a function, I guess it can't go to infinity, so we wouldn't put tangent in there, but certainly our Gaussians are in there, all polynomials are in there. It's a big vector space. You can check it's a vector space. If you take any linear combination of two continuous functions, you get another continuous function. So it's closed under addition and scalar multiplication, whether your scalars reals or complex numbers. Okay, we're going to define the usual inner product. In order to know what the norm means, we need to define our inner product. And of course, our inner product between V1 and V2, or maybe I should call them F1 and F2, since we're really thinking of functions here, right? Would be you take the associated functions, F1, put a star on it, F2, and integrate from minus infinity to infinity, the usual inner product, which then gives us a norm, which is the square root of the inner product of a function with itself. Now, it's not complete. It's a perfectly good vector space, but it's not complete. It has a lot of interesting properties, but it's not complete. Here's my Cauchy sequence, or an example of a Cauchy sequence that illustrates it. It's all functions of this form. And instead of writing it down in some way, I'm going to draw a picture of all the functions we're talking about in here. So here's a function on the real number line. Here is the number 1 over n. Here is the number 1 on the output side of the function. And my function is going to be 0, 0, 0, 0. Then it's going to go linearly up to 1 over n. And then it's going to stay at 1 forever after. Okay, so that function is what I'm going to call Fn of x. And they're going to get steeper and steeper as n gets bigger and bigger. So I'm defining, an infinite collection of functions. A sequence of functions, right? I have F1, F2, F3, F4. That sequence of functions is getting steeper and steeper and steeper. They're all continuous functions, so they're all inside my vector space. The question is, does it converge to something? And your first inclination might be to say yes. What does it converge to? It gets closer and closer and closer to a function that looks like this. Right? It's going to get steeper and steeper and steeper as n gets bigger. Unfortunately, that function that it's getting closer and closer to is not in my vector space. It was a perfectly good vector space. It's just not complete. So there's a hole there, right? And I might have to worry about when I write down an infinite series that the sequence of partial sums does something like this. We don't ever want to have to worry about that. So we're only going to work with complete vector spaces. So for us, it generally, showing one isn't complete isn't too bad. Showing a vector space is complete is actually technically usually really difficult. So we're going to take mathematicians' word for it. First fact is that all finite dimensional vector spaces are automatically complete. Just because, let me just not comment on that, but not necessarily infinite dimensional ones. There are infinite dimensional vector spaces. Here's an example right here, continuous functions that aren't complete. A Hilbert space, which I assume you heard about, maybe it was this word used in modern physics at all, or no? A Hilbert space is our space of functions or vectors that we're going to use in quantum mechanics that has all the nice properties, so we don't have to worry about all these analysis nightmares going on like happened with these continuous functions. It's a vector space endowed with an inner product, and we're always going to use those common inner products we've been talking about, and a norm. The norm's always derived from the inner product as the square root of the inner product of a vector with itself. And it's complete. That's what a Hilbert space means. And so we're going to use Hilbert spaces collections of functions that, comprise a Hilbert space, so that we don't have to worry about when we write down the sum from 0 to infinity Cn psi n of x, where this is a complete collection of vectors. I'm kind of hoping that this sequence of partial sums that's implied here converges to something. If we're talking about a Hilbert space, as long as the Cn's aren't too crazy, right? If I take all my Cn's as 1, it's not going to converge. But if the sum of the magnitude of the Cn squareds is something perfectly finite, then this will converge to something that's within the Hilbert space. And so we don't have to worry about technical details there. That's really all you need to know for Hilbert spaces. Okay, so capital L2 and little l2 are Hilbert spaces, and they're really two ways of representing the same Hilbert space. We already talked about that. If you have a vector, you can represent it by the coefficients or the function of x. They're just two different ways of representing the same thing. All finite dimensional vector spaces are Hilbert spaces. We're going to use them to describe spin later on. And why do we care about them? Well, we're always going to make our states of a quantum mechanical particle to be vectors in a Hilbert space. So we were already familiar with the function representation. We're getting comfortable with the coefficients representation. We're going to do some other representations too. The time-dependent Schrodinger equation describes how the vectors change with time, right? We're thinking of, it tells us how the function changes with time, but each of those functions is a vector. So now we're thinking of those vectors, time-dependent Schrodinger equation is telling us how the vector changes with time, but the vector is represented by a function. And if we have an orthonormal basis, we can write down things like this. And as long as the Cn's aren't too crazy, this series converges, then we automatically know that this is going to be a vector. It's not going to converge to something that's a hole in our vector space because someone's reassured us that we have a Hilbert space. All right, that's a good stopping place right now. And we're sort of, I'll have to look and see if we're butting up against section 3 yet, but that pretty much ends the math subset of this. And now we're going to go back to quantum mechanics and start formalizing the axioms of quantum mechanics. We've been kind of loose about it in chapter 2. You see Griffiths makes claims as, oh, wait, you'll see in chapter 3. Now he's going to try to at least somewhat carefully state what axioms, what exactly we're assuming, and how you compute rho as a function of px and rho as a function of e and all that kind of stuff. All right, any questions before we do